Okay, here we go, ladies and gentlemen. Let's talk about a couple differential equations. First of all, a differential equation is something that involves a differential. Well, what is a differential? A differential is something that has been differentiated. So anything that's been differentiated is a differential. Now, in our particular case, let's use exponential growth as a starting point. Reason to use exponential growth as a starting point is it's because one of those times where we're really interested in rates, rate of growth, rate of numbers, how fast something grows. So for example, E. coli grows at a rate proportional to the number of bacteria present. Now you'll notice a couple key things. Something grows at a rate proportional. So you have y equals kx usually. That's proportional, directly proportional, y equals kx. The difference is it's at the rate proportional. So if it's a rate that is proportional, that means it's y prime because it's dy over dt. It's some certain number of y's per time. So it's a rate that is directly proportional, k times the number of bacteria. Well, if y happens to be used for the dy dt, and that's the rate of the bacteria, the number of the bacteria wouldn't be x, it's going to be y of t. So therefore, our final equation here is y prime t equals k times yt. Now, using that equation, that is a differential. You say, well, great, that's super. That tells me the rate. If I know the number of bacteria and I know the rate at which the bacteria grows, the constant that the bacteria uses, then I can find the rate at which the bacteria is growing at any given time. That's nice, except for the fact that if I want to know the actual number of the bacteria, well, I don't have that. I have the rate at which it's growing at a particular time, not the number at a particular time. So what we need to do is we need to therefore find y by itself. Well, you say, well, that's nice, but I have y right here. Maybe, maybe not. What we need to do is we need to integrate both sides to get rid of the prime. But to integrate this, I need to get the y sub t over here at the y prime of t. So I divide it off. Doing that, that gives me y prime of t over y of t equals k. Integrate both sides. When you integrate this, you have 1 over y of t, so you have the natural log of y of t. That's the integration. Over here, you have k, that's a constant. And so if I integrate that with respect to what? Well, if y is the dependent variable, t would be the independent variable. That's why it's k times t, not kx, because t is the time variable. Plus c, of course, because it's an indefinite integral. Now, I want to get yt by itself, so what I want to do is I want to use the inverse natural log of both sides, and that's going to eliminate the natural log and the inverse natural log, leaving just yt. Over here, though, I have e raised to the kt plus c. Now, you say, well, what is this plus here in this exponent? Well, if I take a look, you agree that x squared times x cubed is really x raised to the 2 plus 3. I just take those two exponents, I would add them together to make 5. Well, I can also reverse it. I can say if I have 7 plus 9 up here, that's the same thing as saying x to the 17th, x to the 16th, and that would be the same thing as saying x to the 7th times x to the 9th. Using that information, I can actually say, well, if I have a plus here, that means I can turn it into two bases with a times between them. So I have e to the kt times e to the c. Now, since I don't want to keep writing e to the c, and e is 2.71828, yada, 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 raised to some constant, it's not a variable, that's all just one big O constant. So I can say e to the c equals, and we'll rename it c1. You will have to actually put the rename over here, or the redefinition, I guess. And that gives you c1 times e to the kt. That is the general solution for a differential equation for exponential growth. Now, it's only growth, however, if the constant does happen to be above 0. If the constant is less than 0, it happens to be decay. So we have greater than 0, growth, less than 0, decay. Okay, using that information, let's actually put it to work. If I have y of t equals c1 e to the kt, the first thing I can do is, given some conditions, my initial condition is at time 0, I have 100 bacteria. At time 60, I have 450 bacteria. So what I need to do is I need to take it from a general equation to a specific equation. And to do that, I'm going to plug some stuff in. If I directly plugged in this term right here, the 60 and the 450, I would say there are 450 bacteria equals C1 E times K to the and 60 minutes. Now the problem is that gives me two unknowns. Well, let's choose the other one. What if I say there are 100 bacteria, C1 E to the K, still don't know C1, but I know that time is 0. Well, 0 times anything is 0, so E to the 0 is 1, so it's 1 times C1, so really I have C1 equals 100. If I know C1 equals 100, I can plug that back into the generic formula. YT equals 100 E to the KT. Well, that's helpful. Now I'm down to one constant, one variable that's independent, one variable that's dependent. Now I can go back over here to my 450 and say 450 equals 100, I know the C1 now, E to the K, and throw in 60 for time. And now at this point, it's fairly simple process of some algebra. 4.5 equals E to the K times 60. And to get rid of the inverse natural log, I'm going to natural log both sides. So I have ln 4.5 equals K times 60. And if I divide both sides by 60, I have some constant. Now, whatever that constant is, I can plug it back in and come up with a general equation. So my final equation would be y of t equals 100 e raised to the, now you could find a decimal approximation for this, or we can just plug it all in as she sits, times t. And now I could say at any given moment, how many bacteria are there? And at any given moment, what is the rate of bacterial growth? So I have both of those functions available to me now. So with that, that is using differential equations to come up with exponential growth. Now, that's not always quite that easy, and it's not always exactly that formula. We have Newton's law of cooling. Newton's law of cooling says that the cooling rate is proportional to the difference in temperature between the item and the ambient temperature. Again, it's not the temperature that's proportional, it's the rate of the temperature is proportional. So again, we're going to come up with a yt over a dt. So we have dy over dt equals K times something. Now, what's the something? Well, the something is the difference in the temperature and the ambient temperature, or the room temperature. And so in that case, you're going to need to do a subtraction between the temperature of the item, YT, minus the temperature of the ambient. So your final equation is y prime of t, the rate at which the temperature is changing, is equal to K times the temperature that it is, minus the ambient temperature. So you can do this problem as well by plugging in the various known quantities to find the unknown quantities. Now, if you wish to do that, that's not a problem. You can plug that in and come up with, first of all, using the initial condition, we would break it all up, integrate both sides, and when you do that, it's going to come out for a general equation of yt equals a e to the kt plus ta. So it's not really that big a deal, and it makes sense that if you're going to turn this around, this minus is going to become a plus. Now, they used a. Okay, we've traditionally been using C1, doesn't make a difference, but you can plug in your initial conditions. This is example 2 in section 1, so you can do that. Example 3 has to do with interest. Well, interest equals principal times e to the rate times time. It's PERT. Well, this is the same situation. It's going to be using integration. So start there.